Welcome back, everybody. So last time in the more trig identities notes, we derived the angle sum and difference identities. Now we're going to look at a couple of quick applications of them, and then looking at the double angle and half angle identities. So zooming in a bit, let's find the exact values of some of these expressions. So for number one, we've got cosine of 165. And so obviously that's not a nice unit circle angle measure that we can kind of picture in our heads. So it's not 45, 60, it's not 150 or 120 or 180, it's 165. So what we're going to want to do here then is rewrite this as a sum or a difference of some nicer angle measures. So 165, maybe we'll note that that's 30 plus 135. It's also 210 minus 45. And there are other variations you could come up with. And note each version of this should look the same, but it can be a sum or a difference. So we'll do the sum version of this expression that we've written above. So using our cosine identity, we know it's going to look like cosine times cosine minus sine times sine. Again, we get the opposite signs for these. So now we just need to evaluate using the unit circle. So cosine of 30 is radical 3 over 2. Cosine of 135 is going to be negative rad 2 over 2. And then sine of 30 is going to equal 1/2. And sine of 135 is going to be positive radical 2 over 2. So what we end up with is, let's see, negative radical 6 over 4 minus radical 2 over 4. And then you could kind of write this in a bunch of different ways. So it's really kind of up to you. If you want to manipulate it more, this would be perfectly fine as an equivalent answer. But you could rewrite it as a single expression or rationalize it if you wanted to. But really, we can just leave it as is. But that is the exact value of cosine of 165. So key idea here is if we don't need a calculator or have a calculator, we can use this to compute exact values of sine, cosine, and tangent. So we'll go ahead and do number 2. So that's going to be sine of 15 degrees. So I'll give you a moment and let you decide on 2 angle measures that we can add or subtract to get 15 degrees. And then we'll use that sine identity. So we'll note we're going to have, let's maybe do the same thing. Let's think of it as a sum or a difference. So if we're doing a sum, getting 15 is going to be tricky, right? So that's going to be, a negative number and a positive number. So yeah, maybe we don't want a sum in this case because that's just going to be overly messy. So let's do this as a difference. So it looks like 60 and 45 degrees would be pretty easy. We could also do pretty much any pairing of angles that are going to be 60 and 35. So we could do 135 minus 120. And so on and so forth. So you could pick a bunch of different ones. My general rule is try to pick the smallest positive angles that will work. In this case, 60 and 45. So we know this is going to give us the sine-which. So we've got sine 60 cosine 45 minus cosine of 60 sine of 45. So we can cosine and sine occur once with each one of those angle measures. And then we'll just evaluate. So we got sine of 60 is rad 3 over 2, cosine of 45 is rad 2 over 2, cosine of 60 is 1/2, and sine of 45 is radical 2 over 2. So we're going to get a similar expression to our cosine of 165, but now we're going to get a positive value minus an expression. So we're going to get radical 6 minus radical 2 all over 4. And note again, you could rewrite this by factoring, so we could do rad 3 minus 1 over 4 times radical 2, or any other variation. And then finally, we've got tangent of 435. So larger angle measure, so a little bit trickier maybe to figure out what two angles we want to use here. So maybe take a moment, see what you come up with. Okay, so looks like 300 plus 135 would work. So maybe that'll be the one that we use here. So let's go ahead and write our identity out. So we'll have tangent 300 plus tangent of 135 over 1 minus tangent of 300 tangent 135. All right, so tangent 300 is going to be negative rad 3 plus tangent of 135 is going to be negative 1 all over 1 minus negative rad 3 times negative 1. Definitely want to be careful with your negative signs here. So maybe we'll write this as negative quantity rad 3 plus 1 all over 1 minus radical 3. But now we'll see, well, there's a whole bunch of different ways we could simplify this using rationalizing if we wanted to. So note this one is perfectly fine. We could write this by distributing the negative sign in the bottom. So we could write this as radical 3 plus 1 over radical 3 minus 1. We could multiply by the conjugate of each and simplify further. So maybe we'll do that here. So maybe we'll multiply by rad 3 plus 1 over rad 3 plus 1. So our numerator is going to be radical 3 plus 1 squared over, and then the difference of squares here will be 3 minus 1, so it'll be over 2. And then again, we could keep going further. So note, there's lots of different ways you can write these expressions. So just kind of be careful of equivalent expressions. All right, so given those use of the identities, let's go ahead and extend it a little bit further. And so we're going to add in what we call the double angle identities. And really this is just going to be, what if x and y are the same, right? So note, for our angle sum and difference identities, we write the sum here with those angles. But what if they're both 30 degrees or they're both 60 degrees? So let's go ahead and see what those will look like. So again, these are just the sum identities where we are using the same angle measure, and we'll get some interesting results from that. So we're going to have, for our sine sum, we'll have sine theta cosine theta plus cosine theta sine theta, but those are really the same thing. So we just end up with 2 sine theta cosine theta, which means that sine 2 theta is equal to 2 sine theta cosine theta. Really important, and the nice thing is that it gives us this 2 theta expression in terms of 1 theta. So in other words, maybe theta is easier to work with than 2 theta. So this is going to make it much easier. It's also going to give us more opportunities to simplify and cancel things. For cosine 2 theta, it's going to look very similar. So we'll have cosine theta times cosine theta minus sine theta times sine theta. But that's going to just give us cosine squared theta minus sine squared theta. So this is Also very useful and also interesting because now we've got squared terms. And by the Pythagorean identity, we can rewrite those squared terms. So we'll note this is kind of the first version of the cosine 2 theta identity. So maybe we'll call this number 1. But there's 2 other common representations. And so we'll go ahead and derive them down here. And our key idea is going to be to rewrite each expression here above with the squared term in terms of the other. Meaning, if I have a cosine squared here, I'm going to rewrite sine squared in terms of cosine squared. So we'll note that cosine 2 theta is cosine squared theta minus 1 minus cosine squared theta, because, again, sine squared theta equals 1 minus cosine squared theta. So that's from the previous notes. And that's just using the Pythagorean identity. But cosine 2 theta is also equal to 1 minus sine squared theta minus sine squared theta. So again, using the fact that cosine squared is equal to 1 minus sine squared. So what we're going to end up with is, on the cosine version of this, we'll get 2 cosine squared theta minus 1. And on the sine version of this, we're going to get 1 minus 2 sine squared theta. So again, similar expressions, right? We still have this difference, but the difference is in a different order depending on if we use sine or cosine. So we'll call this maybe 2, and then this is 3. These are also going to be extremely useful identities. But again, they just derive from the angle sum and difference identity. All right, so we're just deriving it using that first identity we started with. So again, something that you can choose to memorize or know how to derive by using the memorized sum and difference identities. And then from here, we're going to keep going. So we're going to get what we call the power reducing formulas, which are written on the left-hand side here, but we'll derive each one. So let's go ahead and split these up maybe. So we're going to use equation number 2 for this one, and we're going to use equation number 3 for this one. So for number 2, right, we've got cosine 2 theta, so this will be the derivation, equals 2 cosine squared theta minus 1. And what we're going to do is we're just going to solve for cosine squared theta. So the reducing part of it is the fact that this is degree 1, right? Cosine 2 theta is just cosine. But cosine squared theta is degree 2. So I can rewrite cosine squared, a degree 2 expression, in terms of a linear version of cosine in cosine 2 theta. So again, that's going to be kind of the very usefulness here, is writing cosine in terms of different powers of cosine. So we'll start by adding 1 on both sides. So we'll get cosine 2 theta plus 1 is equal to 2 cosine squared theta. And then we'll just divide by 2. So kind of an easier way to write it is cosine squared theta is equal to 1/2 times the quantity of 1 plus cosine 2 theta. And what you'll notice here is that you've got a double angle, half angle identity sort of thing going on, depending on which angle you're focused on. So note theta is half of 2 theta. And then we'll do the same thing for sine squared. So we'll note that using equation number 3, we know that cosine 2 theta, and maybe we'll use the bigger font here, is 1 minus 2 sine squared theta. And then again, we'll do the same thing by isolating the squared term. So we'll have cosine 2 theta minus 1 is equal to negative 2 sine squared theta and then we'll divide by -2. And what that's going to give us is sine squared theta equals, I'm going to use that negative sign to swap the terms here. And then the 1/2 is still just 1/2. So it's going to be 1/2 1 minus cosine 2 theta. So again, writing it with the 1/2 might be a more useful way to think about both of those. And so these are the power reducing formulas, where we can take a squared term and rewrite it in terms of a linear expression, a degree 1 trig expression. And then for tangent, well, what are we going to do for tangent here? It says 2 expressions for half angle, but let's go ahead and look at what tangent of 2 theta is going to look like. So we'll start with tangent 2 theta. So tangent, 2 theta is going to be, again, tangent theta plus theta. So that's going to be tangent theta plus tangent theta over 1 minus tangent theta times tangent theta. But that just means that tangent 2 theta is 2 tangent thetas in the numerator over 1 minus tangent squared. So we'll kind of put that off to the side here. So now we want the half angle identities. And from that, we're going to need the power reducing formulas. So we're going to use these 2 formulas we just wrote above. So we'll start with maybe sine squared theta. So we'll note that that's 1/2 1 minus cosine 2 theta from above. So to get the half angle identities, we just take this power reducing identity and square root both sides. So in other words, sine of theta is equal to the square root of 1 minus cosine 2 theta divided by 2, or 1/2 times 1 minus cosine 2 theta. And what we'll note, though, is that this is going to be plus or minus, right? Because we're square rooting a square, so sine theta might be less than 0. But sine theta might be greater than 0. So it's going to so the plus minus depends on theta. Right, so we're going to have to be a little bit careful here because 2 theta is twice as big as theta, but the sign of the expression is going to depend just on 1 theta. All right, so we've got our sine theta expression, so we'll do the same thing for cosine. So we've got cosine squared theta is equal to 1/2 1 plus cosine 2 theta. Which means that cosine of theta is equal to the square root of that. So these, and I'm kind of writing them both ways. Again, you can think of it as 1/2 times the quantity or dividing by 2. These are the half angle identities. So now the question is, what about the tangent half angles? So we can see that tangent is just going to be the ratio of sine theta over cosine theta. Okay. So then using our half angle identities, we'll have 1/2 1 minus cosine 2 theta over 1/2 times 1 plus cosine 2 theta. So the halves cancel, which is nice. And then we've got this expression. So we've got rad 1 minus cosine 2 theta. Oops. Over 1 plus cosine 2 theta. Now this is still going to be plus or minus. The plus or minus carries over. And again, that plus or minus is going to depend on theta. So if tangent is negative, this square root has to be negative. But on the inside, well, we've got some choices here. We can choose to simplify a bit. And let me add in 2 theta there. So we could choose to multiply by 1 minus cosine 2 theta over 1 minus cosine 2 theta inside of our radical. Or we can multiply by 1 plus cosine 2 theta over 1 plus cosine 2 theta. Excuse me. So depending on which one you choose, you're going to end up with 2 different answers. We'll look at the blue version of this. So we'll have plus or minus the square root of 1 minus cosine 2 theta squared on top, and then on the bottom we'll have 1 minus cosine squared 2 theta, which we can then simplify accordingly. So we'll note that 1 minus cosine squared 2 theta is the same as sine squared 2 theta, since that's just the Pythagorean identity for 2 theta. So this is going to equal plus or minus on top. The square root will cancel with the square, so we'll just have 1 minus cosine 2 theta. And then on the bottom, the sine squared will cancel with the square root, and we get sine 2 theta. So that means that tangent of theta is equal to 1 plus or minus 1 minus cosine 2 theta over sine 2 theta. Or if we did it the other way with the 1 plus cosine 2 theta, we would get sine 2 theta over 1 plus cosine 2 theta. Again, plus or minus. So in class, I'll be giving you kind of a handout with kind of an organizer for these. There's obviously quite a few identities that we've discussed here, so we'll be spending an extra day kind of working on lots of different examples, including these. But the key idea in all of these cases is starting from the angle sum or difference identities for sine and cosine. So note, those are the key identities that allow us to create all of these new formulas. So why don't we organize them here? So for an angle theta, we'll note that sine of theta maybe not that way. Start with the sum and difference. So the angle sum for sine is going to be the sandwich. Again, with the signs on the outside of the opposite angles. And we've got cosine. It's going to be where the cosines stick together. And tangent is going to be the sum of the tangents on top and the difference of the product from 1 on the bottom. So again, these three are the ones to know. These three are definitely the ones to have down, probably memorize. As you practice with it, obviously it'll get better to memorize these. And then from there we can use these to then get our double angle identities. So sine 2 theta equals 2 sine theta cosine theta. Cosine 2 theta equals cosine squared theta minus sine squared theta, or 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. So you can see that the cosine is a bit more versatile because there's 3 components to it. And then we've got the power reducing formulas. And again, those come from the cosine double angle identity. So we know that sine squared theta is equal to 1/2 1 minus cosine 2 theta. And cosine squared theta is equal to 1/2 1 plus cosine 2 theta. And then from our power reducing formulas, we can get our half angle formulas. So we'll have sine theta equals plus or minus the square root, 1/2 1 minus cosine 2 theta. Cosine theta equals plus or minus the square root of 1/2 1 plus cosine 2 theta. And then all of those variations on the tangent. So tan theta is equal to plus or minus the square root of 1 minus cosine 2 theta over 1 plus cosine 2 theta, which equals 1 minus cosine 2 theta over sine 2 theta, plus or minus, or sine 2 theta over 1 plus cosine 2 theta. So again, lots of variations there. So we've got our power reducing here and our half angles here. So half angle, double angle, power reducing. There are lots more identities than just these. So note, these are kind of the starting ones that we'll focus on. You'll see in the textbook there are things called sum to product or product to sum, which again are just simply variations on these expressions where we can take this expression and consider these products on the right with these sums and differences on the left. Those we're not going to emphasize in this course, but they are ones that you'll probably see in the future as well. All right, so getting back to these last few examples here, note we've got some half angle examples. So this expression here we'll note is going to be 45 divided by 2. This is going to be 315 divided by 2. So if these are half angles, we're going to want to use a half angle identity. Tangent of 15 you can write as half angle or sum or difference. And then 7.5, well, that's half of 15. And 15 is half of 30. So it looks like there's going to be a double identity here. So we're going to look at each one and work our way through it. So for sine 22.5, we'll use our half angle identity. So what we'll note, we should just write that down. So we know that sine of theta is equal to 1/2 1 minus cosine 2 theta. So that means sine of 22.5 degrees is 1/2 1 minus cosine. Sorry, the square root of 1/2 times 1 minus cosine 45 degrees. And we'll note this will be positive because sine is positive in the first quadrant where 22.5 is located. So we can just evaluate as is. So we're going to get the square root of 1 minus rad 2 over 2. Maybe we'll use that 1/2 in front, actually. So what are we going to get? So we're going to get 1/2 minus radical 2 over 4, which then we can rewrite as 2 minus radical 2 over 4, which is going to be radical 2 minus rad 2 over 2. So if you can find a perfect square, you're going to want to maybe simplify that out of the expression. But what we'll note here in our expression itself is we are going to have a nested square root that occurs, and that's going to be common with these. All right, so pause the video here, go ahead and give 2, 3, and 4 a try on your own, and then we'll discuss. All right, so we'll write out our cosine identity here, which is going to be 1/2 1 plus cosine 2 theta. So we know that cosine of 157.5 degrees is going to equal the square root of 1/2 times 1 plus cosine of 315. And we know this is going to be negative because 157 is in the second quadrant, so cosine is negative in the second quadrant. So that's going to equal then negative square root of 1/2 plus, well, cosine of 315 again is going to be radical 2 over 2. So we're going to get radical 2 over 4. And so this is going to be very similar to what we had in the first example. So we can make the 1/2 a 2 over 4, and we'll end up with negative 2 plus radical 2 all over 2. For the tangent, I would use the sum or difference identities here. So I do maybe 45 minus 30, or 60 minus 45. Right, some first quadrant measurements would probably be best. So let's do the 45 minus 30. So we'll get tangent 45 minus tangent of 30 degrees all over 1 minus tangent 45 times tangent of 30. So that's going to give us 1 minus 1 over rad 3, which we can write as rad 3 over 3, all over 1 minus 1 times rad 3 over 3. And then we just need to simplify a little bit. So 1 is 3 over 3. So we'll get 3 minus rad 3 over 3. And on the bottom, we'll have 1 minus rad 3 over 3. And that should be plus. We'll get 1 plus rad 3 over 3, which should be 3 plus rad 3 over 3. And this will simplify to 3 minus rad 3 over 3 plus rad 3. And then again, feel free to simplify further with rationalizing the numerator or denominator. Kind of up to you to decide what you want to do there. But you can leave it as long as it's just a single rational expression with a sum or a difference in between terms. For number 4, so we'll note that sine of 7.5 is going to be equal to the square root of 1/2 times 1 minus cosine of 15. And while we're at it, we'll note that cosine of 15 is equal to the square root of 1/2 of 1 plus cosine of 30. So we're going to need to put this cosine in here. So this is going to get quite messy, it looks like. So why don't we do some simplification first then of cosine 15. So if we're simplifying this, we're going to get, and they're both positive, of course, because the angles are in the first quadrant, so that's nice. So this is going to equal 1/2 plus 1/2 times cosine 30, which is going to be radical 3 over 4. So this is going to equal, when we make this into 2/4, 2 plus rad 3 inside the square root over 2. So now we can go back to sine of 7.5. So we're going to have the square root of 1/2 times 1 minus radical 2 plus radical 3 over 2. And so that's going to equal the square root of 1/2 minus radical 2 plus radical 3 over 4, which then we can make this 2 over 4. So we'll get radical 2 minus radical 2 plus radical 3 all over 2. Again, more nested radicals. So a slightly more challenging example, just because you got this layered identity being used multiple times. So this will be the starting point for us. We'll start applying these into identities as well as other expressions. So you'll note on the last page here, we've got some proofs. So in each case here, each one of these proofs, you're going to want to expand these expressions and simplify. So I will leave that to you to do on your own, but you can check the completed notes on the website as well. So that is going to conclude the identities notes here. Again, really the main identities are on this kind of organizer here. There are quite a lot, I understand, but the more you work with them, the more familiar you'll be with them. And just note, these are going to continue to show up in calculus courses and higher level math courses as well, including problems involving engineering, physics, geometry, etc. So again, they're going to be very useful to use in the classes that you take in the future as well. So if you do have any questions, feel free to email me, come by my office hours, and we can discuss. But